How do you define shapes? Well, you start with coordinates that define extremities of a shape. We call them vertices. We collect these vertices in an order. We can assign a number to these vertices in order and define a shape around them. Question here, why start at 0? Well, many early programming languages were designed to be close to the hardware and it aligned well with the machine's architecture. Languages that have been bitten with this bug include C, C++, Python, Java, JavaScript, etc. Memory in computers is stored in contiguous blocks and address of first element is considered as the base address. Using a 0-based index directly corresponds to the offset from that base address. This helps simplify memory address calculation. Take this cube for instance. This cube has 8 vertices. We can see 4 in the front, 4 in the back. The blockMesh utility in OpenFOAM suggests we name the vertices in this order to describe a cube. The vertices are defined, as you can see, and they are defined in such a way that they are in an order. You can see something here in the blocks entry. It goes 0, 1, 2, 3, 4, 5, 6, 7. What does it mean though? The direction of travel going from vertex 0 to vertex 1 is called I. In a similar fashion, next travel from 1 to 2 is called J and the one direction left is called K. The directions can be shown here from vertex 0. You will notice that this description of a block of cube can be done in multiple ways with, of course, its own implication on direction of travel of axes that you define within the geometry. In this case, we've defined the block to have 20 divisions in the first direction, 20 divisions in the second direction, and only 1 division in the third direction. A cube is quite easy to make though. What if the shape is different? Let's take this example. What if I had 2 cubes joined together like this? This essentially represents the backward facing step. Looking at this diagram, we can divide this geometry into a certain number of blocks. This eases up the meshing process where now we can focus solely on number of divisions and ensure structured mesh. Here we have 0, 1, 2, 3, 4 and 5 blocks. So a total of 6. Please note the count of blocks also starts at 0. You can see how the blocks are defined in the blockMeshDict file for this case. Don't be overwhelmed by looking at the number of entries that are given. Let's understand the logic, which is much more important. How can we define boundaries here? Let's remove the blocking for a moment and understand what's happening in this block. This block has 12 vertices as opposed to 8 vertices previously. Let's start by defining this left boundary. Let's call this the inlet. Now I want to explain to OpenFOAM interface that this is an inlet and I would need to explain the vertices that encapsulate this face. The order we do this in can be seen here. The type is kept as patch, meaning I can patch a numerical value to the cells in this face. Next, this face can be called a wall. Since it is situated at the start of our domain, let's call it upper wall startup. The vertices that encapsulate this face can be seen here. Notice the type here is kept as symmetry plane. In CFD language, this equates to flow being a mirror image of flow on the other side of this face. It applies a 0 normal velocity and 0 normal gradient. Similarly, we do the same for lower wall startup. Now here is the upper wall. Notice the type here is wall, that is no slip condition will be applied here. Note the remaining vertices are situated on the other block, which I am not showing in this image right now for simplification. Same goes for the lower wall here. You would have noticed how the arrows here rotate. Notice the red arrows piercing the centers of these rotating arrows. This is called the right hand thumb rule. Imagine the red arrows were your thumb and the direction that your other 4 fingers take is the direction in which you define your boundaries/patches. This is a 2-dimensional study, so we have 2 faces here called front and back, which are assigned a type called empty. Now, this works great for block type geometries, but what about curved bodies? Let's take this cylinder. This cylinder has a curvy body with circular cross section. This can be thought of as a pipe body with an inlet and an outlet with the curved walls encapsulating the fluid within. How do we make mesh for this geometry? Take a look at how we can divide this geometry. We have the vertices in this order 0, 1, 2, 3, 4, 5, 6 and 7. We have 5 blocks with 4 blocks around the curved wall and the 1 block in the middle that is essentially a square. In the same way, we can define the vertices at the other end also. Notice the axis changed. The way we can define the vertices here can be something like this. I've used a bit of trigonometry to define where these vertices will be situated. The blocks can also be made accordingly. The mesh will end up looking something like this. Doesn't that look neat? Notice we have an entry called edges underneath blocks. This is how we define the curves. Arcs between the vertices 1 and 2, 2 and 4, 4 and 7, and 7 and 1. What is this coordinate that we've entered? Think of it this way. Say we have a line joining 2 vertices. If I was to turn this into an arc, I would need to explain where this arc would pass through. That is a third point. That is precisely what this coordinate entry talks about. This is the third vertex through which the arc will pass. So this is what the extremities of our pipe would look like. The inlet and the outlet. The mesh is quite structured in our case. The patches are defined in accordance with the vertices and the order is also derived from the right-hand thumb rule here. But don't you feel this is a bit complicated? There's trigonometry involved. Is there an easier way? Let's take another curved body example here, an airfoil. This is a C-type mesh, domain shaped like the letter C. This is NACA 0012 airfoil, and we have the geometry of this object in OBJ format. OBJ format is surface mesh format. One of the biggest advantages of using C language is we can define certain variables in any file in OpenFOAM to reference back to it. That is exactly what we will do here. We have created a subdictionary called domain where we gave entries that define extremities of where our domain will be as a rectangle. We have also defined the number of cells we want in a certain direction. Now for blockMesh to identify this geometry, we can import the geometry of our airfoil as the tri-surface mesh type. We've also created something called cylinder, which is termed as searchable cylinder. Here we are saying that this cylinder is situated somewhere between point 1 and point 2 with a radius of z max, referenced from domain subdictionary. Think of this cylinder as something that is cutting our rectangle in this manner. So we are left with this blue region that will be treated as our domain now. The vertices are defined here. Notice the keyword project or project here. What does it mean? Look at the vertex 3 and watch what happens to it. Did you see? The vertex 3 slid from the middle of the rectangular face onto the cylinder that we created. This is what the word project keyword actually does. It takes the coordinate we defined, then projects it on top of the domain we want, that is the cylinder. Now talking about the edges, we are just projecting our vertices onto the airfoil and creating arcs directly through the OBJ file that we gave as input. Isn't that cool? We need not create any complicated arcs, we just project on top of the geometry. The end result looks something like this. You can see we have 6 different blocks. We didn't do any arc creation, we simply projected stuff. But Is there an even easier way? We can do it with Python and the VTK module. What is this VTK, you ask? It is the Visual Tool Kit. It's useful in various areas of graphic images, processing, modeling, volume rendering, and scientific visualization. It's quite user-friendly, allows for cross-platforming as long as you have Python. It is widely used and you will have fun with it. The best part being that it's written in C++ and has excellent interoperability with Python. Let's take a look at this piece of code. Don't be scared. We are just creating a line that starts at 000 and ends at -0.700, effectively a line of length 0.7. This code will create a .vtk file that can be viewed in ParaView. It will look something like this, with a length of 0.7 units. When we open the .vtk file in a text editor, you can see something like this. So how does this help us? Well, VTK can be used to interface with OpenFOAM to create some truly awesome geometries. For instance, going back to our example of pipe, this time I can just create a cylinder using our line.vtk file. I just need to create something called an extruded circle around this line with the radius parameter. The inlet and outlet can be defined, or you can choose to not define these here. We can define them during boundary phase. If you pay close attention here, you can see the coordinates here pertain to a square tube inside the pipe. Other vertices are projected on top of the cylinder. To plan this, you can start with a square tube inside another bigger square tube. The vertices of the bigger square tube can directly be projected on top of the cylinder. So essentially this eliminates the need for trigonometry entirely, and also the need to define vertices accurately. You can create these vertices in a plane, project them on top of your geometry. The mesh will look similar to the previous meshes we made. The one major difference you will notice is the density of mesh near the wall. We can control that using grading of mesh. You can see influence of grading here in this simple example of our cube problem. A grading value greater than 1 looks like this, as opposed to grading value of less than 1. It is governed by this formula. blockMesh is actually quite cool and can be used in incredible ways. In a future video, I will showcase a complex geometry meshed using blockMesh in a simple manner. Now, of course, a caveat here is you need the VTK format to get the geometries outlined. This works great for something like a pipe, for which structured mesh is almost always required. Let's discuss some more interesting utilities in OpenFOAM in the next video. Thank you.